start recording on this computer, and I'll post the video so that you can access it later. Let me start with an example that I forgot to show you yesterday. I prepared an example of a ghost contour, the use of a ghost contour to find the inverse the inverse Laplace transform. And so let's consider the inverse Laplace transform here of so let me start the new. Let's see how long I can use the iPad without running into trouble. So the question is finding the inverse Laplace transform of 1 over s minus IA cubed. And well, we have a formula for that was derived back in chapter 4. And if we just apply that here, we substitute for f of s 1 over s plus IU minus IA. And then what we have is an integral on the u plane, and considering u as we're integrating real u, and we can then add a ghost contour like this, and we pick up the pole here, which is over here at a plus is, and but now this is a I guess we'd call it a triple pole, and boy, that's weird. I repeated the same equation, so I'm going to have to fix that. Anyway, this, of course, I cubed is just minus I. And over here, well, what does Cauchy's integral formula give us for this? Well, it gives us 2 pi I divided by 2, and the second derivative of the rest of the function, apart from the pole, the second derivative of this function with respect to u, but evaluated at the pole, which is a plus is. And so the answer then is t squared over 2 e to the iat. And I thought that I would check that by using Mathematica or Matlab, and I thought I'd show you how to do both. In Mathematica, what you do is you enter inverse Laplace transform exactly this way. You put the function f of s here, and then s and t. You don't have to call them s and t, but that's what I did. MATLAB is a little more complicated. You have to tell MATLAB that S, A, and T are not numbers, but are symbolic variables. So you write sims, SAT, on one line. The next line, you don't need a semicolon then. The next line, you say f is the function whose inverse Laplace transform you want, and then you say f equals I Laplace of f. And in both cases, they give you this answer. So that's those are actually three examples. There was something else I meant to tell you. And I can't remember what that was either. So let me just skip now to where we were last time. We were at the method of steepest descent, and I want to just emphasize some of these things. First of all, the idea is that we are doing an integral of this form, and typically an integral of this form is extremely sensitive to the exponent and not very sensitive to h. And consequently, and here we're imagining that r is a real number. Of course, it could be complex, but anyway, we're thinking of it as a real number here, and f is a complex function. And so, what does this exponential look like? Well, you see, f, of course, is u plus iv, but u and v, being the real and imaginary parts of an analytic function, are harmonic functions. That is to say, they have, that is to say, u double prime is zero, and v double prime, u double prime with respect to x plus u, well, maybe I should just say it in formulas. It's that the idea was back here we had harmonic functions somewhere. So the idea was uxx plus uyy equals 0. So consequently, you can't have a maximum or a minimum, and the same thing for the imaginary part. So if we go back then to the method of steepest ascent, you see what we're stuck with is a saddle point. The idea is we're trying to get from a point A to a point B, and the only way to get there is to go over this barrier, and we pick a point in the barrier that's a saddle point. So it's a minimum in one direction and a maximum in the other direction. So it's a minimum this way, and it's a maximum this way. And so what we do then is write, but we've picked a point here where f prime 0 is 0. So the derivative of u and v with respect to x or y both vanish. And so what we do is we can expand f of z as f of w, double w being this point here. That's w. And we can expand, we can write f approximately as f of w plus a half z minus w times the second derivative with respect to w. And that second derivative then is going to be a constant in this approximate integral. And so we let it equal to rho, some real number, positive real number, e to the I phi. And then the tricky thing is we want the line to go through the minimum perpendicular to the to this curve here, but instead parallel in this way. And so in other words, as we vary s along the line, we want z minus w squared f double prime to be negative. And so what we do is we keep this angle here, 2 theta plus phi equal to pi. So this is e to the I pi, which is -1. And so then it's negative. And then f of z is f of w minus a, and we can write it as minus a half rho s squared, where s is where the angles are such that theta and phi are chosen such that 2 theta plus phi is pi. Okay, so the 1/2 here comes from that 1/2. And so now we just substitute that in and do the integration. Well, we're assuming that H of W is smooth and F of W is smooth. So we pull these things out, and the integral that we're doing is just a ds integration. So we're just integrating over S, and S is going in this direction. And so we have e to the minus a half r rho s squared. That's this thing here. ds, that just gives you a Gaussian integral. And the other terms that are this is a constant, this is a constant, so they come out. Theta is a constant by design, by construction, so it comes out. And so that's the answer. It's a little bit complicated like that, but what's useful is to take this e to the I theta and stick it down there. And then when we do that, we see that f double prime is rho e to the I phi, the 2 theta plus phi is pi. And so this structure down here, rho e to the minus 2 I theta, is just minus f double prime at w. And so the nice formula is this. By the way, in most textbooks, this is not used, and instead they leave you with something that looks basically like that. There may have been improvements in the last 10 years, I don't know. A nice application of the method of steepest descent is to Stirling's formula. Now, Stirling's formula is let's put it this way, n factorial exactly is minus 1 to the n times the nth derivative of y to the minus 1 with respect to y, evaluated at y equal to 1. But now we can rewrite that nth derivative as, of course, this integral over z is just 1 over y. And so I'm just writing this in terms of an integral. But now the d by dy just brings down a minus z, and the minus sign is canceled. So we have z to the n, e to the minus z. And we can rewrite that as e to the n log z minus z. So now if we compare this to the standard form for I of r, what we see is that we see that we can set r equal to 1, h of z equal to 1. The saddle point w is where the first derivative of f vanishes. F is n log z minus z. F prime is 0. You see, when you take f here, let me just do it for you. F of z here is equal to n log z minus z. So f prime is equal to n over z minus 1. That's equal to 0 when n equals z. And let me switch to, say, blue or something. And that tells us, oh, that was useful, actually. That tells us then that that z is equal to n, and then that's what we call w. W is the point, is the value of z where the first derivative vanishes. And then the second derivative then, f double prime, is minus n over z squared. And since z is n, that's equal to minus 1 over n, which is this expression. And so we just plug those things in, and we get n factorial as e to the n log n minus n times this integral. But this integral when we do the integral, we just get Stirling's approximation. By the way, we said there that there were only, we assumed there was only one saddle point. If there are several saddle points that are suitably separated, then, and in other words, to do the integral, you have to go over one saddle point, then another, and then a third. What you do is you just take this approximation and just add them together for each saddle point. I'm going to skip the thing on string theory unless there's popular demand on the chat, and let's see, I see something on the chat. Okay, well, that's okay. I should have had this chat open earlier. So let's now go on, I think, to that section, by the way, on string theory was basically just an application of complex variable theory. Now what about differential equations? Well, there are just many kinds of differential equations, first. And secondly, since there are many kinds, there are certainly many different ways to solve differential equations. Moreover, for each kind of differential equation, for each kind or class of differential equations, there are, of course, many different differential equations in that class, and each of them has several different ways of solving it. And so whereas complex variable theory is entirely systematic, everything follows directly from the definition of differentiability. In the case of differential equations, there's nothing systematic. Every differential equation is unique, and there are many ways of solving them, and general methods are not, I mean, they're useful, but only limited extent, and the general methods typically differ from each other. And so since there are many different kinds of differential equations, we have to start with many different definitions, which is, I don't know. Anyway, that's the way it is. I was starting with a differential operator. This thing is an nth order ordinary linear differential operator. It's nth order because the highest derivative is d by d x to the n. It's ordinary because there's only one independent variable, x. And it's linear because derivatives are linear. Okay. Derivatives are linear operator, so L on the sum of two functions is multiplied by two constants is the two constants multiplying L on each of the two functions added together. If all of the HJs here are constants independent of X, then we say L is an nth order ordinary linear differential operator with constant coefficients. And such differential equations can be solved, in principle at least, formally solved by using Green's functions, as in chapter 4, section 8. In other words, and in fact, I can sort of remind you of what that would be. What we want is that the sum, let me try to use the same notation, AJ dj dx to the j, we want that on g of x minus y to be delta of x minus y. So this is the Green's function. And the solution to that is g of x minus y is an integral dk over 2 pi e to the I kx. And now what we have to do is we have to divide by aj ik to the j, summed, j equals 1 to n. And that's because when you differentiate with respect to x, you bring down an ik, and then that gets multiplied by aj, and then you sum them. And so that's how you can solve things like that. Often in physics, we have second order linear differential operators. This is the one for the wave equation in one dimension. Here's a second order linear differential operator, which is written in self-adjoint form. And what you can do is you can always take a second order differential operator and change it to self-adjoint form. And then once it's in that form, it's in a form that's particularly nice for proving things. And so it's nice to have, or it's nice to know what the self-adjoint form is of a particular differential operator that you're dealing with. Now, I refer here to differential equation 7.1. In fact, now that I think about it, 7.1 was not a differential equation, it was a differential operator. So a differential equation of the form L f of x equals 0, this is homogeneous because this is a 0 here. So this 0 means homogeneous. In other words, and it's not just that it's equal to 0, but that L is the differential operator involving just derivatives. If instead we had L f of x equal S of x, this would be inhomogeneous. And because this thing here is a source term. And of course, in physics, we often have source terms. In electrodynamics, the charge density and the current density are source terms for the electromagnetic potential. And in fact, we write AI of x as something like an integral d cubed x ji of y x minus y, and I suppose a 4 pi, and I'm going to put a constant there. I'm going to put a constant, I'm going to call the constant k, because I don't want, c is typically the speed of light, and so I don't want to put the speed of light. I don't remember what that constant is. It's 1 over the electric constant in some cases. Anyway, if you have a differential equation that's linear and homogeneous, then you can add solutions. The point is that, of course, if LF1 equals 0 and LF2 equals 0, then LF is L acting on the two of them, and that's A1 L on the first plus A2 L on the second. And that gives you 0. So the sum is a solution if each of them is a solution. And of course, that can be generalized from 2 to n. And so that makes it possible to find general solutions of linear homogeneous differential equations. For example, this differential equation here, you have sine of kx, cosine of kx, and the most general solution is, I should have said A and B, A sine kx plus A2 cosine kx. Now, remember that when in linear algebra, when we talked about vectors that are linearly independent, I said this was important. And the same thing is true for functions. Functions are linearly independent if the only numbers for which the linear combination vanishes for all x is that all the coefficients should vanish. Otherwise, if you can find a bunch of coefficients such that this is 0, the y's are linearly dependent. And this is important because if you have n linearly independent solutions that are complete, then you have a complete solution of the linear homogeneous nth order ordinary differential equation. You can write it this way. This then is the solution of the homogeneous differential equation. And here the FJs have to be linearly independent if this is going to be a complete solution. Now, at least if it's nth order. Now, when you introduce a source term, the homogeneous differential equation becomes inhomogeneous due to the source term. But now there's you might think, oh, this makes things much worse, but no, it actually only makes things slightly worse. Because if you have two solutions of this equation and you subtract them, the source term goes away. And so the difference of any two solutions of the inhomogeneous equation is a linear combination of the solutions of the homogeneous equation. And so if you have an nth order linear inhomogeneous equation, you can then you can form, it's the most general solution of the homogeneous equation, and that must be the difference. In other words, you can express the difference of any two solutions of the inhomogeneous equation is a solution of the homogeneous equation, therefore can be expressed in terms of a linear combination of a complete solution of the homogeneous equation, this thing. And consequently, just shoving the second one to the right-hand side, you find that every solution to the inhomogeneous equation is a sum of the complete solution of the homogeneous equation plus any solution of the inhomogeneous equation. And what people say is any particular solution of the inhomogeneous equation. All right, so far I've been talking about linear differential equations because these are the ones that we can typically have, can solve one way or another. Nonlinear differential equations are much harder. And a nonlinear equation means that either the function appears in a nonlinear way, like cubed, or the derivative appears squared or cubed, or the function, here, this one, the function appears in a way that is not even algebraic. So there are all kinds of ways for differential equations to be nonlinear. And when they become nonlinear, things are basically, well, they're not hopeless, but the level of difficulty has gone up enormously. Now, of course, these days we have computers, and my impression, frankly, is that you can solve anything numerically. Just a question of how big your computer is and how much time you have and so forth. So now let's look at linear partial differential equations. And an equation like this is, I guess, the most general linear partial differential equation, or actually its most general homogeneous linear partial differential equation. Homogeneous because there's no source term. Everything is linear in F. It's linear because F occurs to the first power, not the 0th power, which would make it inhomogeneous, and not the second or third power, which would make it nonlinear, and not non-algebraically, which would make it a nightmare. But you can have arbitrary derivatives here, and the coefficients need not be constants, they can be arbitrary functions of x. So this is a linear partial differential equation of order n being the sum of the highest derivative, the highest number of derivatives that occurs in the equation. It's a partial differential equation in k variables, and so what do you have? Well, linear combinations of solutions of this equation will still be solutions of the equation because it's linear. And so you have, you can approach this thing systematically by finding one solution and then another solution and a third solution, and you keep going until you have found a linearly independent set of solutions. And this then will be a complete solution of the homogeneous differential equation if you multiply it by arbitrary constants. So that works as before. You can find, you can add solutions. You can find the most general solution of the homogeneous equation. And on the other hand, if you have a source term, well, once again, what you do is you subtract two solutions of the inhomogeneous equation. The differential operator, which now is elaborate, still maps each of them to zero. And so that, I'm sorry, not maps each of them to zero, maps each of them to S. So the difference is mapped to zero. And consequently, the difference of any two functions is a linear combination of a complete set of homogeneous, a complete set of solutions to the homogeneous equation. And so this is the bottom line then. And now, of course, now in a sense, having said this, I could say, okay, well, that's the end. We don't need to do anything else in this chapter because, in fact, we've now, in principle, solved all linear differential equations. And so we're done. But of course, what we have to do is find these actual solutions, find what the FJs are. And that is a tall order. One property of differential equations that's extremely useful is if the, and here we might as well go to the homogeneous case because the inhomogeneous case is a different issue. So if we look at the homogeneous case, we say the linear partial differential equation is separable if you can decompose it into ordinary differential equations. And if you can write the solutions as just a product of a function of the one variable, another function of the second variable, and if you have n variables, then an nth function of the nth variable. And so then basically, if you have a separable homogeneous linear partial differential equation, then basically if it's separable, you can reduce it, or it can be reduced to n ordinary differential equations, which you can then try to solve. And there are many examples in physics, and the separability occurs often because the differential operators aren't arbitrary differential operators. They are differential operators that have a lot of symmetry. And in fact, the separability of a partial differential equation depends upon the choice of coordinates often. And many of the partial differential equations in physics are separable because of symmetry, either rotational symmetry or Lorentz invariance or some other kind of symmetry. Symmetry is your friend. And when you have symmetry, you can, things basically simplify it. I mentioned to you some weeks ago we discussed Bessel's equation briefly, and I said that the solutions to Bessel functions were nightmare functions, not really nightmares, but pretty complicated functions, whereas the spherical Bessel functions were very simple functions. And the reason is that the Bessel functions occur when you have cylindrical coordinates, and that is less symmetry than spherical coordinates. With spherical coordinates, you use spherical coordinates, of course, when you have a problem that has spherical symmetry. And the spherical symmetry makes means that you have simpler solutions, and in particular, the spherical Bessel function, very simple functions there. only a little more complicated than trig functions, whereas the cylindrical Bessel functions are there. I mean, I don't know. I don't know anything that they're similar to. All right, let's go to Poisson's equation. This is basically Gauss's law. And let me just mention that when we think of it as Gauss's law, it's del dot E equals rho over the electric constant. And this is a Maxwell equation in which there's no time variable. You see, in other words, this derivative, there's no dt. And so this is a constraint that has to occur at every time. So it's a constraint as opposed to a differential equation which tells you how E evolves in time. And the same thing is true of another Maxwell equation. Del dot B is 0, there's no time derivative. So these are two constraints. More generally, Maxwell's equations, notice that the spherical symmetry here. This is a spherically symmetric differential operator here. And of course, on the other hand, if rho is, rho is the inhomogeneous term. So there are solutions of this equation that are homogeneous, that are very simple. The inhomogeneous solutions could be very complicated if rho lacks symmetry. Now, in empty space, Maxwell's equations are very nice. They take this form here, and in fact, they imply these wave equations. These are separable in rectangular, cylindrical, spherical coordinates, and these are particular solutions. Then there's the Helmholtz equation is, well, it's sort of the two-dimensional version of this equation. It's this equation, but with a simpler source term. In other words, k squared f as the source term. And this turns out to be separable. We can let f equal to x times y. And when we substitute it in here, we see that this operator acting on it, well, the d by dx squared just acts on the x, and the d by dy squared just acts on the y. So we get these two terms, and they have to be equal to k squared xy. And now what we do is we divide by xy. When we divide by the product xy, the y cancels here and the x cancels there. And so let me switch maybe to green. And so if we have this equation, which now is minus y x double prime minus x y double prime equals k squared xy, we divide by xy and we get minus x double prime over x minus y double prime over y is equal to k squared. And now this, you see, is just a function of x. This is just a function of y. And the only way this equation can be true is if minus x double prime over x is equal to something. And what did I call it I called it a squared. And this is equal to just y double prime over y. And so when you add them together, they come in with opposite signs. No, actually, no, I'm sorry. I was going a little too fast there. So let me go back to green, comma. Y double prime minus y double prime over y is equal to b squared. And now what we want for this equation is a squared plus b squared is equal to k squared. So that's basically how this works. And so what you get then is xa of x times yb of y are both solutions of this differential equation. And for example, one can have xa of x equal to e to the IAX, yb of y equals e to the iby. And now the general solution of this homogeneous equation is e to the IAX plus iby. And so that's xa of x times yb of y. And then one can take integrals or linear combinations of them that solve this equation, in other words, k squared. So in other words, what we do is we want to restrict a squared plus b squared to equal k squared. And so what we would say is that we could integrate dA setting, well, let me just get rid of the last couple of things. dA e to the IAX plus I, and now we want this b to be k square root of k squared minus a squared y, and I don't need one of these parentheses. So this is a this is probably basically a general solution. And of course, we can multiply that by an arbitrary function f of a. So this is something like a general solution. So that was Helmholtz's equation in rectangular coordinates. We also have, we can do it it separates also in polar coordinates. In polar coordinates, what we have is the three-dimensional Laplacian, but without the z derivative. And so we have this expression here. And now we write f as rho times phi. We substitute in here, and then we get rho squared p double prime over p plus rho p prime over p plus rho squared k squared equals. And then what we really get is rho squared, rho double prime over rho plus rho prime over rho plus rho squared k squared plus phi double prime over phi equals, and what was the original differential equation? I guess that's k squared. Well, it's just k squared. And so what one, oh wait, I have a k squared there. Well, it'd be something else on the right-hand side here. Let me just say k prime squared. K prime squared. Anyway, then dividing by rho phi, we get, well, what we see is that this part is just a function of rho. This part is just a function of phi, and this part is a constant. And so we can then set this rho part equal to a constant, and then the phi double prime over phi part equal to a constant. But those two constants have to add up to whatever the right-hand side was. I think it might have been k squared. And anyway, the question then is, what is n? Phi n is e to the in phi. That's an obvious solution to this equation, equal to n squared. What is n? Well, usually we want, as we go around phi from 0 to 2 pi, we want to get back to the same number. And typically, if all values of phi are physical, in other words, if the points described by all values of phi from 0 to 2 pi, if they're all in the physical region, then we need n to be a constant, so that e to the I 2 pi n is 1 again. And that means that n has to be an integer. And so our equation then at that point becomes rho squared p double prime plus rho p prime plus rho squared k squared p kn equals n squared of p. Actually, well, I was calling it rho because it's capital Greek rho. Although I guess if it's, anyway, the Bessel function of the first kind obeys Bessel's equation, and that's what this is. And so what we have then is that the solutions of this, of the Helmholtz equation in cylindrical coordinates then, and just in the plane, the two-dimensional Helmholtz equation, is the nth Bessel function of argument k rho plus I n phi. And in 3 dimensions, it's a similar business. In rectangular coordinates, we have this nice symmetric Laplacian, and we write the solution as x, y, z. Laplacian hits it, we get all these expressions. That's k squared x, y, z. Dividing by x, y, z, we then say xa is e to the IAX and so forth. YB is e to the I BY. ZC is e to the ICZ. And then we take a linear combination of the products, but we have to have a squared plus b squared plus c squared equal to k squared. In cylindrical coordinates, we have the previous problem plus rho f, the second derivative with respect to z. We divide by rho phi z, we get these equations, and then we argue that, it turns out that we can use the nth Bessel function, but now a more complicated argument, the same phi, and then an obvious z dependence. And alpha can be either real or imaginary, or in general, it could be complex. So if we have here k squared greater than alpha squared, this is the ordinary Bessel function. But when alpha squared is bigger, it's the modified Bessel function, in. So just to have real argument, we call it in. And then you can also separate it in spherical coordinates. And when we do that, we wind up with the theta function is the associated Legendre function, which we'll see in a later chapter. If phi from 0 to 2 pi describes the physical region, then m has to be an integer. Otherwise, m can be anything, just any real number, I guess, or whatever m squared work. However, m squared works in this equation. Anyway, this theta then is e to the im phi times what's called it's an associated Legendre function, and that involves an e to the im phi times a function of sine theta and cosine theta. We'll discuss that later in chapter, I don't know, 9 or so, maybe 10. probably maybe 9, I think. The radial function then has to obey the radial equation, which is left, and it has an L coming from the angular equation. And the solution then is a spherical Bessel function. And as I said, this is a much simpler function and than the cylindrical Bessel function. And so looking at it, let me just see if we can tell just by looking at these equations whether it's simpler. So we have here for this one, it's x squared JL prime plus x squared minus L plus 1 JL equals 0. So that's the spherical Bessel function. And back here, we had a cylindrical Bessel function somewhere. Well, that was, I think, the inhomogeneous case. Well, I unfortunately didn't write it down. Let me find it for you over here. Right. So the Bessel function is this more complicated function. So that's Jn double prime plus 1 over, in this case, Z, Jn prime plus 1 minus n squared over Z squared, Jn equals 0. And if we multiply through by Z squared, we see it's Z squared Jn double prime plus Z Jn prime plus Z squared minus n squared Jn equals 0. So is it obvious that this is simpler than that? Well, the second terms are pretty much similar. That is to say, this term and this term are plausibly the same. What's simpler here is, you see that you can't write these two in this nice form, because if you had Z squared Jn prime, that would give you 2Z Jn prime plus Z squared Jn double prime. And so that's not the same as this. So I guess it's that first derivative term that is what simplifies everything. Anyhow, in relativistic field theory, there's an equation called the Klein-Gordon equation, and that involves a differential operator, which is the Laplacian minus the second time derivative. There's a notation that's in use in relativity, which is that, all right, let me try to tell you what the notation is. X upper I is what you think it would be. What you think it is. In other words, x1 is x, x2 is y, x3 is z. X0 is typically c times t, where c is the speed of light. In some cases, x0 is just t, and in some cases, one sets the speed of light equal to 1, so one doesn't even see the c. But, and in nice notation, x lower 1 is also x lower 2 is also y, x lower 3 is also z. But x lower 0 is minus ct. So that is what happens when you lower indexes or indices. Similarly, partial x1 is written this way. Partial x2 is that, which can also be written as d sub y. Of course, in general, 0, 1, 2, and 3 can represent arbitrary coordinates. They don't have to be rectangular. And d0 is partial with respect to ct, or partial with respect to x0. But now, if we raise these indexes, we get partial 1. Well, it's the same as partial 1. Partial 2 is the same as partial 2. Partial 3 is the same as partial 3. But partial 0 is minus d0. So that's the convention that is used in relativity half the time. And it's used in general relativity almost all the time. In special relativity, one sometimes, what we say here is that there's a metric eta, which is minus 1, 1, 1, 1, and this is what we use to raise and lower indexes. There's another convention which uses eta prime, which is 1, minus 1, minus 1, minus 1. This has more minus signs, and I think is a basically dumb convention. People like it in particle physics because then they say p prime squared is then p0 squared minus p vector squared, and that is e squared minus, let me just for the moment use units where c and h bar are 1. This is e squared minus p squared, and this is equal to m squared. So what they like about that is that this is positive, and this thing looks positive because it's something squared. Whereas in the nice notation, with fewer minus signs, p squared is equal to minus m squared. Again, in units with h bar and c equal to 1. Anyway, the Klein-Gordon equation is basically this differential operator on something equals 0. And sometimes one puts in a squared mass term. In fact, typically one puts in a squared mass term. And here we have the triangle. The Laplacian is often written as a triangle. Well, this 4-dimensional Laplacian or D'Alembert is written sometimes as a square. And the solutions to these are quite simple. It's px, which you can write as p lower a x upper a, and that's just p dot x minus p0 x0. And so if a is and b, a is some function of px being this, then d by dx k is just pk times the derivative of b, and so the D'Alembert minus m squared is p vector squared minus p0 squared minus m squared, and then what have I done here? This is p squared minus m squared equals 0, right? Because now something is screwed up here. That's minus m. Right, this should have been a plus sign, actually. So I screwed up. This should be a plus sign. That should be a plus sign. That should be a plus sign. That should be a plus sign. Because then p squared is minus m squared, and the m squared cancels. That's with this notation. With the more common notation, this is the equation. Anyway, field of a spinless boson, for example, one of the 4 components of the Higgs field could be written this way, mass m. It satisfies the Klein-Gordon equation, again, because it's written this way, and you have to get the Klein-Gordon equation straight. I'll fix this up and put it on the web page, the class web page tonight. And so you'll see what the sign is, plus or minus here. But that's sort of irrelevant from the point of view of differential equations. Anyway, the key point here from the point of the quantum field theory is that A and A dagger satisfy commutation relations like these, and they make the field satisfy canonical commutation relations. And what's kind of nice about these things is that they are the analog of the equal time commutation relations of quantum mechanics, which are these. And so what you get then for these A and A dagger, and if you have these commutation relations with the delta function, then the field commutes with itself at equal times. The field time derivatives commute with themselves at equal times. And this one is thought, here the idea is phi dot is thought to be pi, the conjugate momentum. And phi, the commutator of phi with phi dot at equal times is I times the delta function. Again, these are with h bar equal to 1. For photons, what you have in the Coulomb gauge, for example, is an expansion like this, where this is a 4-vector, but it's a 4-vector that in which A0 is a function of the charge density. The 3-vector potential, well, actually, so this is a 3-vector, but it satisfies the equation del dot A equals 0. So you have to have here P dot E equals 0. So as to satisfy this gauge condition. This is the Coulomb gauge condition. You then have the annihilation creation operators once again satisfying these relations, and but the Coulomb gauge condition makes the commutation relations of the fields more complicated. So instead of a nice delta function commutation relation, you get an extra term because of the Coulomb gauge condition. And no matter if you use a different gauge, you get a different, this thing still is not so simple. Dirac's equation, well, something that's interesting here is suppose Dirac's equation is solved by 4-component spinors that satisfy this equation. So A goes from 0 to 3, M is a constant, H bar and C are 1, so forget about them. And alpha and beta go from 1 to 4. And these gammas then are 4x4 matrices. In fact, there are 4 4x4 matrices called the Dirac matrices, the gamma matrices. And so this is the Dirac equation. And it looks like this in ordinary notation. And there's also a notation that people often write slash notation. So it's d slash plus m chi is equal to 0. D slash just means gamma a and the 8th partial derivative. And the 4 Dirac gamma matrices are defined by 10 rules, and their anti-commutators add up to twice eta. And then the question is, what's eta? Well, let's use the nice eta which has 3 plus signs and 1 minus sign. I'm going to skip this. This is the rest of this I'm going to skip because it's not really germane, necessary for understanding differential equations in general. So let's go to first order differential equations. This is a dy dx equal to some f of xy, which you can write as a ratio of p to q, or we can write that as p dx plus q dy equals 0. This is a first order ordinary differential equation. And so sometimes it's easy to solve. Well, it's easy to solve in particular if in fact p is just a function of x and q is a function of y, because then the variables in the equation are separated. And then what one does is one just integrates this equation, and the integral of that equation, in fact, if I write it like this, you can see both. So the integral of this equation is that, and f and g are known functions, so you're given them, so you can do the integrals. So then what do you have? You have a function that involves x and y, but that's the solution. That gives you the solution. You do the integration, and then you solve what is y as a function of x. And just to make sure that this is not so obscure, let me just try to do it on the fly. Suppose it's x squared dx plus y dy equals 0. Okay. So then, as I said over here, we just integrate that. So we get 0 is the integral of x squared dx. Let's go from 0 to x plus integral 0 to y dy. So this will be 0 is equal to x cubed over 3 plus y squared over 2. Well, this tells us that y squared over 2 is equal to minus x cubed over 3, or y is equal to the square root of minus 2/3 x cubed. So that's our sort of weird solution to a problem that I just, invented there on the fly. There's something called Zipf's law, which is an amusing example. It's not, well, it's an amusing example. I learned about it from Gell-Mann. A guy named Auerbach noticed that many quantities are distributed in a funny sort of way, that there were n of them these are things that depend upon x, okay? So how many are there of this kind when x has a certain value? Well, the density of items is dn is minus a constant a times dx over x to the k plus 1. This is separable. It's also separated. If k is not 0, we integrate it to this. And if k equals 0, well, it's n is equal to minus a log x, which is there over some constant. The case k equals 1, it turns out, occurs a lot in actual real life. And it's called Zipf's law. And for Zipf's law, I don't know how in God's name you pronounce Zipf. Anyway, it's k is equal to 1, so x is equal to just a over n plus c. With c equals 0, it applies approximately to the populations of cities. If the largest city in a country has population x and the population of the second largest has population x over 2, third largest x over 3, fourth largest x over 4. Of course, these are approximate values. It also applies to numbers in a table of some sort. So if we let x equal to, what do we have? We have x is equal to a over n for c equal to 0 and k equal to 1. We have a is equal to x equals a over n. The rank n of the number x is approximately a over x. So now we can compute the number of numbers that occur with the first digit d and k trailing digits. And so what you find is a over d times 10 to the minus 4. I'm sorry, a 10 to the minus 4 over d plus 1. What this means is that if the first digit is more likely to be a 1 than a 9 by a factor of 45. And so the German government actually uses this to catch people who are cheating on their taxes, because if they find somebody who's citing charitable deductions that start with an 8 or a 9, instead of with a 1 or a 2, that turns on a red light and somebody looks at the return a little more carefully. Here's the logistic equation, which is a famous equation because it has a simple solution. What we do is we can just rewrite it as ADT is this, so it's separated. We can then rewrite that in this way, and we can integrate it, and we get then that f of t is e to the t minus some particular t over 1 plus e to the a t minus some particular t. And in particular, the sigmoidal, do I have a, no, I don't have a figure, so I'll draw you a figure here. The solution like this, what it typically looks like is something like that. And in this region here, where this is the value, say, t sub h, and this is a value, this value here, this distance, maybe I'll use red. This distance is equal to 1 over a, then and that's what this solution looks like. And in particular, it applies to drugs, poisons, whatever, almost any cause and any effect. Often, many causes have effects that look like this. If you have if the cause is very, very small, whoops, let me go to green. If the cause, what happened here? If the cause, let's say, is quite small, the effect is quite small. If the cause is quite big, the effect is big. And in between, in the vicinity of TH, the effect rises rapidly with the cause. And so this is, vitamins, say. Tiny bit of vitamin does you a tiny bit of good. The right amount of vitamin does you a lot of good and gets you up to here, but tons of vitamins is no use at all, no extra use at all. Here's something interesting, which I've never seen this in print. The Hamilton, this way of solving the anharmonic oscillator, this is something I borrowed from supersymmetry. In fact, from Ed Witten's notes on supersymmetry. And whereas but this is just scalar, the scalar part of supersymmetry. So I've got a Hamiltonian here of the form W minus IP, W plus IP. Again, H bar is 1. Oh, why H bar came in? What do you know? Anyway, so you multiply this out and you get W squared, a commutator, and P squared. And so, and the commutator of W with P gives you a derivative of W. So it looks like this. And so this we can write as P squared over 2M plus V, where V is this funny potential. You see, it's a very funny potential, W squared minus W prime, and where W prime is the derivative. And the remarkable thing is that you see, we factored H like this. And so H on some state, we can say, well, maybe W plus IP annihilates the state. And that would be the ground state, because the lowest possible value of the energy would be when W plus IP annihilates the state and gives you 0. And so that differential equation is here. It's W times psi of x plus H bar times psi prime of x. And so we get the differential equation psi prime over psi, or d log psi dx is minus W over H bar. We integrate, we get psi of x is psi of 0, exponential minus 1 over H bar, integral 0 to x of Wx prime dx prime. So this is then the wave function of the ground state with energy 0. And that's as long as psi is square integrable. And it will be if, for example, W, the highest power of W is an odd power. For example, if W is just linear in X, we get the harmonic oscillator. But on the other hand, if W is quadratic in X, we get the ground state. We get this ground state. Well, what did I say? W is cubic instead of linear. We get this ground state, which is the ground state of a quartic Hamiltonian. And we can calculate all sorts of things about it. Well, we're out of time. I must tell you something important. The chairman has decided that I must now teach in person. And so I'm going to teach in person next week. This means then that it won't be online. We're not going to have any videos. It'll just be like any other class. We're going to meet in room 1140. I'll get to the question in chat in a moment, but let me finish by saying that we're going to be meeting then at 5 o'clock on Tuesday, room 1140. I'm going to wear a mask. I hope you guys all wear masks. And of course, I can't require you to wear masks. Anyhow, we'll just have a normal class. You can see whether you prefer normal classes to Zoomed classes. They have the advantage that I'm there in person and it's easier to ask questions and talk. Whether you'll find it better or not, I don't know. We'll see. But to answer the questions here, yes, it'll be the same time as there'll be the usual posted time, 5 o'clock Tuesday and Thursday, 5:30 on Wednesday. And on Monday, I want to discuss the grading. In fact, I think I'm going to let you guys vote on the grading. And I'm going to give you probably 3 choices, all on the homework, half on the homework, half on the final exam, 3/4 on the homework, 1/4 on the final exam, whatever. And I think I'll just go by whatever the majority decision is. I did promise you in the beginning that it'd be all homework, and then I found that there's this horrible Indian company that sells solutions and therefore has made life impossible for anybody teaching anything. And so then I decided, well, it'd be unfair to grade on the homework because students with lots of cash can just buy the solutions to every problem, and students without so much cash just have to do the problems themselves and so forth. So So I don't know. On the other hand, well, I don't know. Frankly, as I've said to you many times, I would much prefer to teach without any grading system at all. Now, to get back to a question here, the gamma looks like a rank 3 tensor. Okay, great question. All right, so let me switch to black. Gamma 0 is minus I 0, 1, 1, 0. Gamma vector is minus I 0, sigma minus sigma 0. The sigma are the three Pauli matrices, which are 0, 1, 1, 0, comma, 0 minus I 0, and 1, 0, 0, minus 1. And here, this is actually 4 by 4, because this guy here is the 2 by 2 identity matrix. The gamma matrices are 2 by 2. So I. Okay, so I think I've answered Shravan's question. So you're right, it is a rank 3. In some sense, it's a rank 3 tensor, but the way we normally think about it is 4 by 4 matrices. Okay, so I think I've said everything. I've made some announcements on the class webpage, which I've now called a syllabus. When I was a student, I never, ever looked at the syllabus for any course I taught. And I don't think that any course I'm sorry, I never looked at the syllabus for any course I took. And I don't think that any course I took had a syllabus, or if it did, I was unaware of it. But somehow people have become fascinated, bureaucrats have become fascinated with syllabuses lately. So my class webpage I've now called a syllabus, and it has everything you need to know. The only thing I haven't been able to put on the syllabus is how far I will get in the course, because that involves the future, and I can't predict the future. I may catch COVID and die in November. So this is uncertain. So I think it's silly to say when we're going to finish what subject. All right, that's enough for today. I'm going to end the class. If there's a last minute, I'm going to end recording at least. So here, let me stop recording.